When working with water specifically, we're going to focus on the different phases of this substance. And every substance exists as a solid, a liquid, and a gas. And it can be shown using a heating curve, which we have already studied previously when we looked at states of matter. And so now we're going to use the different states of water to help us figure out how much heat was added as a certain amount of temperature was increased. And we are going to focus specifically on the spaces where the heat and temperature are increasing. So that would be on all of our sloped sections. So we've got ice, water as a liquid, and gas. Okay, solid, liquid, gas, remember from previously. And then those spots where it levels off, the temperature stops changing because that is where the phase change actually occurs. And so just to remind you, 0 degrees Celsius is the top of this line here because that's where the melting point starts, and then 100 degrees Celsius is the top of the water section. That's where it will start to change into something else. So if you are ever working with a problem that tells you, a certain temperature change, you can actually map out where it is, what state it's in, and then use the corresponding specific heat. That's what's listed here. So if it's in this section, we are going to use the specific heat of ice, which will vary between the states. Now we have specific heat of liquid water and specific heat of gas water or gaseous water. And those will be important for solving our heat equation, Q equals mcat. Still using this guy to solve our problems. So number 1 says a beaker containing 150 milliliters of water is heated from 5 degrees Celsius to 75 degrees Celsius. How much energy was absorbed by the water as its temperature increased? We have how much energy, that's Q, that's what we're finding. We have temperature change, and we have volume, which for water, we know that 1 milliliter is 1 gram. If you forgot that, then I'm telling you now. Anytime you see milliliters of water, you can just call that grams. They're the same. So now we have enough information to solve for our delta T, because we always know the specific heat of water, ice, or steam based on the heating curve above. On the heating curve underneath number 1, this is just to help you trace out where the temperature change happened. So we've got 5 degrees, that's going to be a little bit above 0, up to 75, not quite to 100. So we are going to be in this section here, which will have the specific heat of water through that whole section. Now we're ready to plug in for our equation. Q equals mass, specific heat, and our temperature change going from 5 to 75, that's a 70 degree increase. Now we just need to find that product, and that comes to be 44,000 joules. Or you could also write this as 44 kilojoules, because remember, kilo is the metric prefix for 1,000. Both of these would work, but the actual answer you get from your calculator is 44,000. You can just change it with the units if you'd like to make it kilojoules. Just a reminder of how to convert between the two. Number 2 is now going to focus on an ice slab going from -15 to -10. So we're going to be in this section, different specific heat. So let's look up at our heating curve. 2.1 is the specific heat of ice. We're still finding energy, so that's Q. We have mass, and we have delta T. So again, same thing, Q equals M C And then it went from -15 to -10, so 5-degree increase. Find this product, and we get 16,000 joules. Or again, you could write 16 kilojoules, just based on that unit, whatever you prefer. And we'll do one more together before I let you loose to do 4 through 8, following the same process. A pot of water with 350 milliliters, remember that's grams, there's our mass, placed on the stovetop at 20 degrees, so that's about here. How much energy will have transferred to the water when it reaches 100 degrees Celsius? So now we're in this section. That's liquid water. It has not boiled yet. It's just reaching that boiling point. We've got mass, we've got temperature change, and we've got specific heat. So plug them in. MC delta T is an 80-degree increase. Multiply them together and we get 119,000 joules, or 119 kilojoules. Again, whichever one you prefer. And the reason that I'm getting numbers with 1,000 after them instead of other numbers is because I'm rounding for significant figures, but your numbers should round to the same number if you were to round them. For the following problems on the page that I said, now you get to do it. Now you're solving for other variables than just Q. This one you're finding the final temperature, so you'll want to plug in. I might help you set this one up because this one can be a little tricky. But then number 5, you're solving for mass, so just solve for M. Starting temperature for 6, how much energy for 7, and energy for 8. So you're just solving for different variables. I'll help you set up number 4, and then we'll call it on this video. So we have mass, we have energy transfer, and we have a temperature that we're starting with, which we'll call TI, T initial. If we're starting at 105, that means we're going to be in this section. That's our vapor or steam section. And we can plug in here Q equals MC, and then we have delta T. So if we solve this guy for delta T, we will get, let's see, 3.2 times 2 is 6.4. And divide. And you get 33.6. Okay. So, if our starting temperature was 105, we need to have a 33.6 degree increase, because that's what our delta T is. So we're just going to add our 33.6 to the starting temperature. 105 plus 33.6. After this increase, we should have an ending temperature of 138.6. I'm going to round that to 140 for significant figures. Okay. Another way you could do this is if you just immediately put in TF minus TI for delta T, and then you'll end up doing the same process. You'll add that initial temperature over. Both give you the same answer, it's just a different way of writing the work out. But there's how you would solve for the final temperature. Finding that increase and then applying it. You do the rest, and we will meet tomorrow on Zoom at 1 o'clock.